Good morning. Welcome to the section 3.4 lecture video. Today we're going to talk about uh, the derivative as the rate of change. So we're going to look at one of the really important application areas when it comes to derivatives, which is rate of change. So just like with all our other videos, you have the note sheets can either be found in Blackboard or on my MATLAB. So you can follow along using those, or you can just take notes in a normal notebook. But let's go ahead and look at section 3.4. So we're on page 21 in the note sheets. So we're just going to start off with a few definitions here, and then we'll get into applying those definitions in a moment. So the instantaneous rate of change of f with respect to x at x equals 0 is the derivative, right? And that's the definition when that limit exists. So suppose that an object or body considered as a whole mass is moving along a coordinate line and s-axis, usually horizontal or vertical, so that we know its position s on that line as a function of time. So notice we're going to use s for displacement, and that really is just because we use d for a lot of other stuff here, or for position, I mean, because we use p for a lot of other stuff as well. So the displacement of the object over the time interval from t to t plus delta t is delta s, which is f of t plus delta t minus f of t. So let's break down some of these symbols. Again, so this symbol, the triangle looking thing, remember, is the Greek letter delta, which simply means change. So if we start at time t, then t plus d delta t would just be whatever t is after a certain amount of time has elapsed. So if I start at time 3 and I let the time change by 4, then t plus delta t would be 7. Similarly, down here, we're saying the change in position from is simply wherever it was at the end of the time interval minus where it was at the beginning. So displacement is simply about where you start and where you end, not necessarily what happens in the middle. If, for example, I were to go out, if I started at my front door to my house and I were to walk around the block back to the front door of my house, my displacement would be 0. But I've obviously walked a distance greater than that because I walked around the block. But the displacement would be 0 because it's how far are you from where you started. The average velocity of the object over the time interval, which we write v sub av, is the displacement divided by the travel time. So delta s divided by delta t. Velocity in general, which more specifically could be called instantaneous velocity, is the derivative of the position with respect to time. If a body's position at time t equals s of f of t, then the body's velocity at time t is equal to the derivative of that. Okay? And speed is related to velocity. Speed is the absolute value of that derivative. So one of the important notes here is that velocity and speed are different in that velocity has direction and speed does not. So velocity can be negative. For example, if I drop something, its velocity would be negative because it's going down. Okay. If we take the derivative again, so velocity is the rate at which displacement is changing. So that's why it's the first derivative. If I want to know the rate at which velocity is changing, we call that acceleration. So acceleration is the derivative of velocity with respect to time. If a body's position at time t is s equals f of t, then the body's acceleration at time t is a of t equals the derivative of the velocity function, or the second derivative of its position. Okay, so acceleration is simply how fast is the velocity changing. And then the last one is called jerk. Jerk is the derivative of acceleration with respect to time. So j of t is equal to the derivative of a, or the third derivative of its position. So jerk is how fast are you accelerating. Okay. So that's the idea, some of the definitions we're going to look at. So now let's look at some applications to go along with that. So it says, given the positions s equals f of t of a body moving on a coordinate line with s in meters and t in seconds, find the body's displacement and average velocity for the time interval. Okay, so that's the first thing we want to do. So to do those, there are no derivatives involved, right? To find the displacement, which is delta s, we just take f of t plus delta t minus f of t. So in this case, we start out at 0 and we end up at 3. So it's going to be delta s equals f of 3 minus f of 0. Okay, so then we just simply have to plug those in. So this would be 3 to the 4th over 4 minus 3 to the 3rd, not over anything, plus 3 squared minus 0 to the 4th over 4 minus 0 cubed plus 0 squared. Okay, and so the best way to deal with that is just put in our calculator. So if I go to my class calc app, I can just put that in. So, and I can ignore the 0, right? Because those are just going to be 0. So 3 to the 4th divided by 4 minus 3 to the 3rd plus 3 squared. Okay, so that's 2.25. And in a lot of cases here where we're doing applications, we're okay with using decimals. So that would be 2.25 meters. So that's the displacement. And then it wants the average velocity. Well, the average velocity, right, is delta s divided by delta t. So in this case, the average velocity would be 2.25 divided by 3. So the average velocity, so we can just do that in here, 2.25 divided by 3 is 0.75. And the units on that will be meters divided by seconds, right? Because I took, on top I had meters and I divided by 3 seconds. Okay, so that's part 1 for this first problem. Okay, so now let's look at part 2. So part 2 says find the body's speed and acceleration at the endpoints of the interval. Okay, so in order to find that, we need to know the velocity and acceleration equations, which means we need to find the first and second derivative of s. Okay, so velocity is going to equal s prime. So in this case, the derivative velocity would be 4t to the 3rd over 4 minus 3t squared plus 2t. Okay, and if we simplify that, that's going to be t cubed minus 3t squared plus 2t. And then the acceleration equals the second derivative of that. So that means we need to take the derivative of the velocity. So that would be 3t squared minus 6t plus 2. And so now it wants us to tell us the speed and acceleration, at the endpoint. So that means I need to find v of 0 and v of 3. And then I need to take the absolute value of those because they want the speed. So that's going to be 0 cubed minus 3 times 0 squared plus 2 times 0. And so that'll be 0. And then this one will be 3 cubed minus 3 times 3 squared plus 2 times 3. And the absolute value of that, so even if it's a negative answer, it'll be positive. So that's what? 27 minus 27 plus 6. So that's 6. And then it wants the acceleration. So we need to find a of 0, which will be, so 3 times 0 squared minus 6 times 0 plus 2. So that's 2. And then I need to find a of 3, which is 3 times 3 squared minus 6 times 3 plus 2. And so that one's 27 minus 18, which is 9, plus 2 is 11. Okay, so there's the idea. So here are the answers for part 2. And then for part 3, it asks, when, if ever, during the interval does the body change directions? So what has to happen to change directions? Well, in order to change directions, what you have to do is, if I'm moving forward, I have to momentarily stop and then turn around. Okay. Well, what happens at that point where I stop? Well, if I'm stopped, I'm not moving. So that means my speed or my velocity is 0. So to answer this question, what we want to know is, when is the velocity equal to 0? So now we can just take this derivative we already found, which is t cubed minus 3t squared plus 2t, and set it equal to 0 and solve. So factor out a t. And then you can set each one of those equal to 0. And then we can factor. So two numbers that multiply to get multiply to get 2 and add to get -3 are t minus 1 and t minus 2. So we get t equals 1 and t equals 2. So t equals 0 is one possible answer, but that's an endpoint. So we're not changing directions there. That's just where we started out. Okay. But then the other two work out. Okay. So where the velocity is 0 are t equal 1 and t equal 2. So those are places that we change direction. Okay. So that's the idea there. Okay. So let's go ahead and try one more together. So the first thing you want to do is you want to find the displacement. So to find the displacement, you just do delta S. So you want to do f of, in this case, f of 0 minus f of -4. So delta S would be 25 over 0 plus 5 minus 25 over -4 plus 5. And so that's going to be 5 minus 25. So the displacement is -20. Okay, meters. Okay, and actually, real quick, let me go back to this last problem for a second. I should put units on these things. So time is in seconds, and then velocity is in meters over seconds, which is speed is meters over seconds, and then acceleration is meters squared over seconds. Okay, so those are the units on those answers. Okay, so now back to this problem. We found a displacement. So now what we want to do is we want to find the average velocity. So the average velocity is delta S over delta T. So the average velocity here would be -20 divided by the time, which is 0 minus -4. So that would be 4 seconds. So the average velocity is -5 meters per second. Okay, so that's part 1. Then part 2. What we need to start out by doing is we need to find both these derivatives. Okay, so I can start out by finding the velocity, which is s prime. So that's going to be the derivative of 25 over t plus 5. So I need to use the quotient rule. So that's t plus 5, the bottom, times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom square. Okay, so the derivative of 25 is 0. So that means this entire first part's going to go away, right? Because 0 times t plus 5 is 0. And the derivative of t plus 5 is 1. So negative 25 times t plus 1 times 1 is negative 25. So this is going to be negative 25 over t plus 5 squared. And then we can do the acceleration. So the acceleration is the second derivative. So I have to use the quotient rule again. I'm doing the derivative of this. Okay, so that's going to be t plus 5 squared times the derivative of negative 25 minus negative 25 times t plus 5 squared all over t plus 5 squared. Okay, and so this one's going to take a little bit more room to do. First thing I have to do is I'm going to need to, I can notice first that this part goes away, the part on the front here, because this derivative, the derivative of negative 25 is 0. So this is all just 0. So that can go away. But on the second part, in order to do this derivative, I'm going to need to multiply it out. So negative becomes positive 25 times the derivative of the bottom. So times the derivative of t squared plus 10t plus 25 all over t plus 5 squared, which is t plus 5 to the fourth. Okay, so now let's come over here and keep going with this problem. So the now we do the derivative of t squared plus 10t plus 25. So that's going to be 25 times 2t plus 10 all over t plus 5 to the fourth. And now we can simplify this a little bit, because if I factor out a 2 from right here, then this becomes 50 times t plus 5 over t plus 5 to the fourth. And now I can cancel out 1t plus 5. So this is 50 over t plus 5 to the third. Okay, so this is my equation for velocity, and this is my equation for acceleration. So now I need to do the same thing I did in the previous problem. I want to find the acceleration and the velocity of the endpoint. So I want to find the speed, and the acceleration. So the velocity at negative 4. Okay, so that would be the absolute value of negative 25 over negative 4 plus 5 squared. So negative 4 plus 5 is 1. 1 squared is 1. Negative 25 divided by 1 is negative 25. The absolute value of negative 25 is 25. So 25 meters per second would be the speed at 4. And then we can do the velocity, the speed at 0. So same idea. So negative 25 over 0 plus 5 squared. So 0 plus 5 is 0. 0 plus 5 is 5. 5 squared is 25. 25 divided by 25 is 1. Negative 1. Absolute value of that is 1. So it'd be 1 meter per second at 0. Okay. And then we want to do the same thing for the acceleration. So the acceleration at negative 4. So plug that into the acceleration equation. So that's 50 over negative 4 plus 5 cubed. So negative 4 plus 5 is 1. 1 cubed is 1. 50 divided by 1 is 50. So 50 meters squared per second is the acceleration at negative 4. And then we could do the acceleration at 0. So negative 25 over 0 plus 5 cubed. So 0 plus 5 is 5. 5 cubed is 125. 25 divided by 125 is 1/5. So this would be negative 1/5 meters squared per second. Or negative 0.2 if you wanted to use decimals. And then the last thing it asks us to do is when, if ever, does this interval change directions? Well, once again, to do that, we want to take the velocity and set it equal to 0. So negative 25 over t plus 2, t plus 5 squared equals 0. And this will never equal 0. Okay, because no matter what, there's no way to divide 25 by a number and get 0. So this is undefined. So that means in this case, for part 3, there is nowhere that this is equal to 0. Okay. Undefined. So this one does not change directions. So that's the idea. Now that we've done a couple of these, why don't you all take a few minutes, pause the video, and try the one here at the bottom. Okay, so now that you've all tried this one at the bottom, let's go ahead and run through it together real quick. So start, same as the other problems, by finding the displacement. So delta S, in this case, would be 6 times 6 minus 6 squared minus 6 times 0 minus 0 squared. So if we do that, 6 times 6 is 36, minus 6, you can put it in a calculator. Delta S is 0. So the displacement here is 0. Does that mean it didn't move? No. It means that it started and stopped in the same place. So at time 0 and time 6, we were at the same position. Okay, so that's why the displacement over that time interval was 0. So therefore, if our displacement was 0, that means our average velocity is also going to be 0. Because of how we calculate it, delta S divided by delta T. So the average velocity is going to be 0 over 6, which is 0 meters per second. Okay, so on average, because there was no displacement, my velocity was 0. But all that really means is the velocity going to and away from the point just canceled each other out to end up with that velocity of 0. Okay, so then for part 2, we want to start out by finding the derivative. So the velocity equals S prime. So in this case, the velocity would be, the derivative of S would be 6 minus 2t. And the acceleration equals the second derivative of S. So the acceleration would be negative 2. Okay, so this has a constant acceleration to it. Okay. So what we want to know is what is the velocity then at the endpoint, the speed at the endpoint. So v of 0 and v of 6. So the velocity at time 0 would be 6 minus 2 times 0, which is 6 meters per second. And the velocity at time 6 is 6 minus 2 times 6, which is negative 6 meters per second. And then the acceleration at time 0 is just negative 2. And the same at 6, right? Because it's constant. Acceleration equals negative 2. So no matter where we are, the acceleration in this problem would always be negative 2 meters squared per second. And then the last thing here is where, if at all, is the velocity equal to 0? Well, I can tell you right now that the velocity is going to be equal to 0 somewhere because we go from a positive velocity to a negative velocity, which means we have to cross the x-axis for that to happen. So we figure that out by setting the velocity equal to 0. So negative 2t equals negative 6, so t equals 3. So at time equals 3 seconds, the velocity was equal to 0. Okay. And that's the idea. So that's how we're using these derivatives in these problems. So now, let's take this a little further and let's look at some more explicit application problems. So a 45 caliber bullet shot straight up from the surface of the moon would reach a height of S equals 832t plus minus, and this should be not 26, but 2.6 t squared feet after t seconds. On Earth, in the absence of air, its height would be S equals 832t minus 16t squared in t seconds. How long will the bullet be aloft in each case, and how high will the bullet go? Okay, so question 1 is, that one thing we need to know is what happens. So aloft means in the air. So we want to know how long is the bullet in the air. So we want to know, well, what happens to the equation when the bullet is at ground level. Okay, and the answer to that is that the position equals 0. Okay, and actually to save on space, let me write this over here. So that's what happens, S equals 0. So that's where we're starting that, and that's where we're stopping. So what we want to know is, when does S equal 0? To answer how high will the bullet go, we need to know, well, what happens at the highest point? Well, what happens at the highest point? Well, if you throw something up into the air, when it reaches that top point, it turns around, right? It was going up and now it's coming back down. Well, what did we say in the last set of problems happens when you change direction? The velocity is equal to 0. Okay. So to answer the first question, all we have to do is set the equations equal to 0, right? We just need to let S equal 0. So to answer the first set of questions, we're just going to do 0 equals 832t minus 2.6 t squared. And so let's go ahead and do that one. So factor out a t. Okay, and set those equal to 0. So t equals 0, and 832 minus 2.6 t equals 0. So at time 0, the height is 0, but that doesn't really matter. That's the beginning of the problem. So it starts there. But then we want to know the answer to this other piece to answer the question. So negative 2.6 t equals negative 832 divided by negative 2.6. And we get t equals 320 seconds. So on the moon, the bullet would take 320 seconds to come back down to ground level. And then we can do the same thing for Earth. Okay, so for Earth, we could do, here, I'll just write it down here and do it fairly short. So it's going to start out basically the same way, right? So you're going to factor out a t. So we're going to get t equals 0 and 832 minus 16t equals 0. So once again, this t equals 0 is just the beginning of the problem. So when it leaves the gun. And then over here, we'll subtract 832 from both sides. And then divide by negative 16. So 832 divided by 16 is 52. So on Earth, the bullet would only take 52 seconds to come back to the ground. So that's part 1. Now to do part 2, what we have to do is we have to start out by finding the derivatives, right? Because I want to know what happens when the velocity reaches its highest point. The velocity is equal to the first derivative of the position vector. So on the moon, the first derivative of the position vector would be 832 minus 5.2t. And so now we want to plug in 0 for velocity and solve. So 0 equals 832 minus 5.2t. Add 5.2t to both sides. And then divide by 5.2. And for that one, when you do it, what you're going to get is 160 seconds. Okay, and then we can do the same thing on Earth. So the velocity on Earth is equal to the first derivative of its position vector. So the velocity equals 832 minus 32t. Set that equal to 0. So 32t equals 832. Divide by 32. And we should get t equals 26 seconds. Okay, so that's the idea. Okay, so if at this point you wanted to pause the video, you could, and then we'll try this one together in a second. Or actually, let's just, either way. If you pause it, great. If not, we're going to go through this one together now. So a rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second at about 86 kilometers an hour reaches a height of s equals 24t minus 0.8 t squared meters in t seconds. Find the rock's velocity and acceleration at time t. In other words, we just need to find the derivatives, right? So velocity equals the first derivative. So velocity would be 24 minus 1.6 t. Okay. And then the acceleration is equal to the second derivative or the first derivative of velocity. So that would just be negative 1.6. Okay, so the acceleration due to gravity on the moon is negative 1.6 meters per second, and the velocity at any given point is 24 minus 1.6 times the time of the problem. So then it asks, how long does it take the rock to reach its highest point? Well, we talked about this in the previous problem. To figure that out, you let velocity equal 0. So 0 equals 24 minus 1.6 t. Add 1.6 t to both sides, and then divide by 1.6. So 24 divided by 1.6 is 15. So it takes 15 seconds for it to reach its highest point. Okay. And then the last question is, how high does the rock go? Well, if we know at what point it reaches its highest point, we can use its position function, s equals 24t minus 0.8 t squared, to figure out when that happens by finding s of 15. Okay, so we can go back to our calculator and plug that in. So 24 times 15 minus 0.8 times 15 squared. And so we get that it reaches 180 meters. So S of 15 would be 180 meters. Is the highest point it reaches. Okay, so let's try a couple more together, and then we'll be done with today's video lecture. So although the November 1959 Kilauea eruption on the island of Hawaii began with a line of fountains along the wall of the crater, activity was later confined to a single vent in the crater's floor, which at one point shot lava, is what that's supposed to say, 1,900 feet straight into the air, the Hawaiian record. What was the lava's exit velocity in feet per second and in miles per hour? So if V naught is the exit velocity of a particle of lava, its height t seconds later will be s equals V naught t minus 16t squared. Okay, so that helps us get this equation. So s equals the exit velocity, 1,900 feet per second, t minus 16t squared. Oh, sorry. Never mind. That's not right. Okay, but what we okay, what we have is a height. A position that we can plug into that. Okay, but we still have two variables left over. Well, what happens at the highest point? Well, at this highest point, 1,900, we know that the velocity equals 0. Okay, so one thing we can do is we can use the velocity function for this. So we've got s equals v naught t minus 16t squared. Okay, and so what we can do is we can take the derivative of this to find v. So that would be v naught minus 32t. And then what we can do is we can get a second equation that we can solve for t in terms of v naught, because we know in this case 0 equals v, right? Because we're at the highest point, so the velocity is 0. And now we want to solve this for t, so we can substitute it into our original equation and solve for V naught. So this would be 32t equals V naught divided by 32. So V naught, t equals V naught over 32. And now I can plug that in to this equation. So 1900, let's actually rewrite it like this. V naught times V naught over 32 minus V naught over 32 squared equals 1900. So that's V naught squared over 32 minus V naught squared over 32 squared. (32 squared) is 1024. Okay, and so now we can get rid of the fractions by multiplying both sides by 1024. Okay, so that gives me 32 divided by, this will be 32 V naught squared minus V naught squared equals 1900 times 2400, which is 1,945,600. Combine like terms, so we get 31 V naught squared equals 1,945,600 divided by 31 to get V naught squared equals a decimal. So I'm just going to write it like that for now. And then take the square root. Okay, so let's go ahead and put that in the calculator. So square root of this. And so we get 250.52. So the velocity is 250.52 feet per second, right? Because that's the units we were in. We had 1,900 feet, and all this is in seconds. So the exit velocity was about 250 miles per hour. Now what we want to do is they also, feet per second, sorry, not miles per hour. Now we want to change that to miles per hour. So the key is we've got 250.52 feet per second, and we want to change it in miles per hour. So what we need to do is we need to change out these units. Well, to change feet into miles, I know there is 1 mile in every 5,280 feet. So that equals 1, and this will cancel out my feet and change it into miles. Then I need to change my seconds into hours. So there are, well, you could do this in two ways. The easiest way is to go to seconds first. So there are 60 seconds in 1 minute. So go to minutes first. And then there are 60 minutes in 1 hour. And so the minute unit cancels, the second units cancel, and we'll be left with our miles per hour. So you want to take your answer, okay, of 250.52, divide it by 5,280, and then multiply it by 60, and multiply it by 60 again. And so we get 170.81. So 170.81 miles per hour. So about 171 miles per hour is how fast the lava left the tube. Okay, so that's the idea of what we're looking for here. And that's how you convert units. So let's try one more together, and then, like I said, we'll be done for today. So the number of gallons of water in a tank t minutes after the tank has started to drain is Q of t equals 200 times 30 minus t squared. How fast is the water running out at the end of 10 minutes? And what is the average rate at which the water flows out during the first 10 minutes? Okay. So, in order to figure out, there's two things going on here. There's an average rate and there's an instantaneous rate. So to find let's start by finding the average rate. So to find the average rate, what I need to know is how much water is in the tank at the beginning and at the end. So we need to find Q of 0 and Q of 10, and then we're going to subtract their differences, right? That's how we do average rate of change. So Q of 0 would be 200 times 30 minus 0 squared, and after 10 would be 200 times 30 minus 10 squared. So Q of 0, let's just go ahead and put these in the calculator. So 200 times 30 squared is 180,000. And 80,000. So this one is 180,000 gallons, and then this one is 80,000 gallons. So then the average rate of change, the average rate at which the water is flowing out, would be delta Q over delta T. So that'd be 180,000, minus 80,000 over 10 minus 0. So that's 100,000 divided by 10, which is 10,000 gallons per minute is flowing out. So that's average. So that's just using average rate of change. But to do the instantaneous, we need the derivative. So you need to find the derivative of Q with respect to T. So the derivative of this function. Okay? And to do that, using what we know now, we're going to need to multiply this out first. So d of dt is 200. And we could actually use the constant multiple rule to bring the 200 out front. And then I need to multiply out this derivative. So that's 30 times, 900 minus 60t plus t squared. And then we can take that derivative. So that's negative 60 plus 2t, and then multiply that by 200. So that's going to be 400t minus 12,000. And now we want to know, so that's my derivative, and we want to know how fast is the water running out at time t. So now I just plug 10 into that. So 400 times 10 minus 12,000 is 4,000 minus 12,000. So this will be negative 8,000 gallons per minute. And I noticed an error that I did up here. This answer is right, except that it's supposed to be negative because I put these in backwards. Remember, whenever you're using average rate of change, you have to make sure that the things on top and bottom line up. So Q of 10 has to go above 10, which is the 80,000, and Q of 0 has to go above 0. So this should be negative 100,000, which means the answer should be negative 10,000 gallons per minute. Okay. So there are a bunch of examples about average rate of change. Good luck working on the homework. Don't forget to do it. Don't put it off to the last minute. And if you have any questions, feel free to contact me and we can talk about them.